Hey there, it's Chem Coach Powers, and today we're going to be talking about water. There's a couple really interesting and fun properties about water that make it very unique, actually make it so that this awesome planet can exist the way it does with the life that it supports. So we're going to talk a little bit about that and a couple other really interesting properties of water. Some of this stuff will be reviewed, but maybe you haven't thought about water in this way before. It's a very short section in your book. We're on 10.5, but it is nevertheless a really good section in your book. It's properties and structures of water. We today want to explain how certain properties of water are determined by its structure and your criteria for success today, given a property of water, like the high boiling point, the density of the solid form, for instance, describe how the structure contributes to determining that property. Okay. All right. So first of all, you've seen water many times before. There it is. That is the structure of water, the structural formula of water. And you can see the Lewis dot structure basically there. And that particular structure is what gives water some of its unique properties. Now, things to think about with water is the hydrogen bond, right? Hydrogen bonds are super significant. That the water molecule is a polar molecule, and of course that it's bent. So when it orients itself, you can see these water molecules here orient themselves. Now notice that we have the negatively charged parts of the molecules aligning themselves to the positively charged parts of the molecules. And that's important because that alignment is what's going to help us understand some of their properties. First of all, water has a high boiling point. In other words, it takes a lot of energy to get that to change from the liquid state to the gaseous state, right? And what you're doing when that happens, like if this is our liquid water, you've got to basically break these bonds in order for the molecules to be able to escape. Okay, and so breaking those bonds is taking energy. And so in order for it to turn into a gas where it can escape, it's got to break those bonds. It takes a lot of energy. All right, remember that something that's very unique to water is that its liquid form is more dense than its solid form. In fact, 4 degrees Celsius water is the water that has the greatest density, believe it or not. All right. And so as you start dropping below 4 degrees Celsius, you're actually starting to have that molecule expand a little bit and it becomes less and less dense. Now, this is one of the things that makes life on Earth survivable, because if you have water that actually is more dense as a solid, as a solid than as a liquid, then as the ice starts to form, the ice just starts to fall, and you end up burying the various different types of life forms that you might have that live in the oceans, right? And without our ocean life, we would not be able to, exist on this planet the way we do. So water's properties that allow it to be less dense in the form of a solid allows for that layer of that ice to be on top. And then, as things freeze, you don't just keep piling and piling ice down on ice and then make the planet colder and colder, right? All right. So remember that there is lots of space between molecules. We want to think about the space between those molecules, okay? So here I've got a little picture of density, right? This is liquid water. These molecules are moving about, right? Think of that kinetic molecular theory. They're moving about. And notice the size of our letters here, D, M, and V. All right, kind of watch what's happening as we go from there. As we change to ice, then you'll notice we have these hexagonal patterns. And this is kind of the cool thing about water is that it forms these little hexagons, okay? And notice how what happened is my density decreased, my little d got smaller there, and then our volume got bigger. Okay, so big V there. So as volume increases and our mass stays the same in a certain sample of water, our density is going to be getting smaller. So we have these hexagons. Now this is cool because you may have never paid attention to the shape of ice, but when you look at the shape of ice, you're going to start seeing lots of little hexagons in there, right? Crystalline water is forming structures of hexagons. Now let's take a look at that. All right, so here I've got, if I kind of connect these dots, you can see that I've got a hexagon. Whoop, whoop. Not exactly good drawing there. But let's say I'm connecting any other kind of similar dots inside here. Now you can see that if I have this, little line in here, I've got a hexagon, and I've got some hexagons better than others, right? Well, let's say I connect the dots that are part of this plane. Okay, so we're just kind of, and I'm not doing a very good job. Okay, we're getting there. And Okay, so we've got 6,000 sides there with my bad drawing. All right, but that's kind of the idea. Isn't that neat to be able to see all these different little layers of hexagons inside there? And you can do that over and over and over again. The reason that it's forming these layers of hexagons is because the actual structure of the hydrogen and oxygen bonds orient themselves in such a way where they form these little hexagons. Isn't that fascinating? Isn't that fun? Yes, I'm glad you agree. This is always a picture I think is kind of cute. You may have looked like this when you were a kid and you saw ice expanding out of a jar the first time. I know you probably wouldn't be this excited now. Me, I might be exactly that excited. Look at the ice. But what you can see here is the expansion, right? So if I started with some liquid and you guys I'm sure have done this, and you put some liquid in the freezer, you forgot about it, and it expanded, whether it be your water, and all of a sudden the water bottle is now distended, or maybe it actually broke a bottle. You have this exact same thing happening, and this is why it's actually dangerous in the winter and to let your pipes freeze, because those pipes are actually going to break, even though water is like this soft, or I can crack ice and I can't like crack a piece of metal, but that water will expand and it'll actually destroy your pipes. It'll ruin those pipes. It's actually stronger than the pipes in that sense. As it expands, it's going to just break them. So it's important to make sure that you drain out those pipes every year as wintertime approaches and you've got freezing temperatures coming. All right, so here's an example of what it looks like if we have some ice, all right, that floats on top. It's a less dense material, right? So our solid is on top of our liquid. But look at paraffin. Paraffin is quite a bit different. Paraffin solid, here's all the solid parts. That paraffin solid is sinking to the bottom because it's more dense. And again, most substances are going to be more dense in their solid form than they are in their liquid form. And so you can see why it might be here if you look at the molecular structure. Whereas over here with our water, we have these hexagons that are forming, and it creates these little shapes. But with our solid paraffin, you can see that they kind of align, and they are able to just kind of line up on each other and pack on each other, a little more close packed structure. And when it becomes a liquid, they're moving around, and so they jumble around and push off each other, and they kind of create some extra spaces. So again, that's paraffin. Other substances work a little bit differently, but kind of cool to be able to see, a solid, which is typically the case, being more dense than the liquid. So what do you think is filling up this area? Okay, what's filling up the area in here? It's a good question to think about here. What is in that little space? All right, there's tiny little people with their heads, with very big eyes, and maybe some bloodshot eyes. I don't know. He's like, let me out. I've been in here for weeks and I can't. No. Anyway, sorry, getting a little crazy here. Is there little people inside? No, of course there's not little people inside. Okay, let's see what options. Do you think there are? There's air inside the little spaces between these molecules? Do you think there's water vapor? Or do you think there's nothing in the spaces? Okay, this is something that's kind of important to think about, because when we think about the density of water, what is creating that smaller density? Are we filling these little spaces with air, or are we filling them with nothing? Now, in this particular model, I'm looking at a molecular model, aren't I? This is actually a molecular model, and I can see to the level of molecules. And if there's nothing in there, if there's no molecules in there, then that's the answer, all right? If there's nothing in there, there's no molecules. Otherwise, I'd see the molecule. I'd have a little model of, a little oxygen molecule here. Yay, here's my little oxygen. Okay, no, it's not there. So in this case, we're basically saying that these are spaces that are filled with nothing. Now, obviously, I believe that, and again, this is my personal belief. I've seen, this is an answer from the text says that there's nothing in there, but I absolutely believe that there's probably, in a real situation, sometimes there's a chance for some, oxygen molecules to work their way through, and there would be some air inside there. Okay, so my personal answer is, yeah, there's going to be some air in some of these, but in this particular model, we have a model that shows us to the molecular level, and there's no molecules in there. So we have to say, hey, there's nothing in there. All right. So anyway, another cool little fact about water. All right. We talked about in the phase diagrams last lecture, we talked about, what happens when you increase the pressure with certain things, right? How when you increase the pressure on a lot of liquids, you're going to turn them into a solid. Well, look at what happens when you increase the pressure on water. Now, I will tell you that they've done studies since this kind of typical textbook situation has been shown. They've done studies showing that there are tiny, tiny, tiny little films of liquids on the surfaces of most solids. So I will say that this kind of thing can happen to varying degrees on a lot of different solids because of pressure. But the idea of why it works so well to have a frictionless environment with escape blade is that that extra pressure from the escape blade causes these molecules to kind of get broken off, right? And so those little molecules of water get broken off and create a small little thin layer of liquid, right? So you have this liquid film. And so that is kind of like a bunch of tiny little, ball bearings that are all just right on top of the solid. And so you get this super, super slick environment, which of course we know, right? We've been on ice before, and we know we know that it can feel very, very slick. And so kind of cool to think about that as well. Okay, another little part of water that we want to talk about briefly here is the idea that water absorbs tons of heat without changing the temperature much, because this is regulating the temperature of our planet. Now, here we've got somebody that's walking across a set of hot coals, right? These are burning coals that this person is walking across. You can see a little fire there by their feet. Well, the reason that this can work is because your feet have some water on it. In fact, in this picture right before, you might have had this person, just dipping their feet in water, and so now they're walking across, and a tiny, tiny, tiny little layer of water on your skin can create what's called the Leidenfrost effect. And basically, it means that that water is changing into a gas. All that energy is going into changing the water into a gas, because it takes a lot of energy to do that. That means that the energy isn't going directly into your foot being heated up, right? And your foot has got a ton of water in it, right? Your body is mostly made up of water as well. And so you're going to see that all this energy is going into transforming water into a gas. And so you can actually do something like this without the amount of pain that you might think you'd have. But again, dipping your feet in water right before you do this would be super important. They don't necessarily tell you to do that. And I'm not saying they do it every time, because you do have some water in your feet that, especially if you're sweating out of your feet because you think you're going to die, then you're probably going to have a pretty good coating. But again, you got to go fast. You can't just sit in there and you're like, put your feet in there like, yeah. I mean, it's going to burn you. So it's got to be a quick kind of thing. All right. All right. In fact, if you guys have ever seen I'm sorry, I got to do this. If you guys have ever seen Mythbusters, you like watching Mythbusters, one of my favorite episodes of Mythbusters is when they're trying to figure out if they can put their finger into molten metal. And so they take these hot dogs and they start dipping these hot dogs into molten metal to see what's going to happen. And sure enough, they kind of verify that the Leidenfrost effect is in play, and tiny little, tiny little areas of air, little pockets of insulating air are created around your fingers as you put your fingers in this molten metal. Now you have to do it fast. Again, it's got to be, and that's what they do. And again, watch the episode. Don't try this on your own, but watch them do it. It's really fascinating. Same effect occurs when you take really hot water and you put it onto a pan, and it like spins around. Right? When you do that, that's the same kind of thing that's happening. It's a Leidenfrost effect. It creates a small little bubble of air around that droplet. And so, it takes a while for it to actually evaporate out, just kind of hovering over the pan. Really fun to see. All right, anyway, water can hold on to the heat for a long time. That's a good concept. And again, why our planet is able to stay so stable. Because think about it, our planet is mostly made up of water, right? Like 75% ocean, I think, or something like that, right? Covered with water. And so all of that water, it takes a while for that sun to heat it up. But once it's heated it up, it holds on to it. And so, yeah, we've got these storms that are raging across the planet because water is heating up and cooling down and creating storms. But it also just stabilizes the overall temperature of the planet. Like, think about a planet like Mercury. Okay, or like the moon, if you're looking at the moon. What happens is you go from the cold side to the dark side, right? As you go from the sun side to the dark side, you're going from where you've got a lot of heat to a lot of cold. Like the temperature extremities on Mercury are huge, like hundreds of degrees Celsius between their light and their dark, right? And we don't have that on Earth because it's going to take a long time to cool down the planet. So by the time we rotate back around, we're already starting to heat up again, and we haven't really cooled down that much. And this is also why a lot of times in those areas around, the cities that are around a body of water, large bodies of water, you will see that those cities will maintain their climate much more steadily and have much less extreme or many fewer extreme shifts in temperature than a city, for instance, like Denver, where we're surrounded by rock, right? Well, the temperature in Denver can go and fluctuate a lot because we don't have water regulating and keeping our temperature pretty stable. Okay, but you go to a coastal city and their temperatures are not fluctuating nearly as much as ours. They'll stay hot and they'll stay cool, right? But they don't go up and down nearly as much as we do here in other cities that have kind of like those environments that are mostly surrounded by rock. All right, so heat of fusion. The heat of fusion is a term which basically says this is the amount of heat that's released when a given quantity of material freezes. And again, remember I said that freezing, we talked about this before with the orange orchards, freezing is actually an exothermic process. Okay, so the heat of fusion is how much energy is given off when you have a certain amount of material freezing. And so fusion is kind of weird, but right, we're not talking about nuclear fusion, but that's the term that they use for heat being given off. And then they have heat of vaporization. And this is the amount of energy that is given off, or the amount of heat that is given off when a material is going from the liquid to the gaseous phase. Now this, sorry, not given off. In this case, it's required. So we said it one way the other time, but this time it's required, right? So, come on. So before we had released, okay, and that's for heat of fusion. And then for heat of vaporization, you have the amount required. And this is what explains why water can put out fires. I love this one, right? Because, I don't know, we always just think like, well, water and fire, they're like opposites, and like, they're gonna beat each other up. Well, the reason that you are able to put out a fire is because water has a high heat of vaporization. What that means is that it's going to take a lot of energy to get that water to turn from the liquid phase to the gas phase. And guess what? A fire needs a lot of energy to continue its cycle of destructing, right? To continue its cycle of burning, it's got to have a lot of energy to keep that carbon bond breaking up and burning things. So if you can put water on it, then you are basically cooling down the fire. You're slowing down the reaction so that eventually the reaction stops, because it just can't sustain itself, because all of its energy is going into boiling off the water basically, and it can't sustain its own reaction of carbons breaking up from each other. So anyway, so cool to think of the fact that fire actually gets put out by water due to heat of vaporization, and the fact that water takes a lot of energy to cool off. A lot of energy to boil. All right, so let's look at this. This is basically a diagram that shows us the different phases. Okay, you can see I have ice here. Okay. It's a phase, type of phase diagram, but it's not giving you all the different phases in the way that we were talking about before. And then we have the liquid, kind of writing sideways here, and my little marker is doing some weird stuff. And then we have the evaporation. And then if we wanted to go and show something further, we would have a line over there that goes up. Okay, but I want you to pay attention to how much energy we have in each of these. This is 335 joules, okay? The amount of energy it takes to go from ice that is, and again, what are we dealing with? We're dealing with a certain number of grams, okay? And so we just have a particular quantity of this substance. It's gonna take 335 joules to take solid water and turn it completely into liquid water, okay? All that energy is going into melting it. And then it takes 418 joules to get that liquid from 0 degrees Celsius to 100 degrees Celsius. And then look at this. Remember I said water has a high heat of vaporization? It takes 2,259 joules to take that same quantity of water and turn it from a liquid at 100 degrees Celsius to, and it's over there somewhere hiding off on the screen, to a gas at 100 degrees Celsius. Now notice the temperature isn't changing at all, right? So this is solid at 0 degrees Celsius and a liquid at 0 degrees Celsius. And up here we have liquid at 100 degrees Celsius and gas at 100 degrees Celsius. So we have not changed the temperature at all. But look how much energy it took, right? With the same quantity of water, I can change that energy. I could change that water from 0 to 100. I could get it to the boiling point with 418 joules. But look how much more, like more than 5 times the amount of energy would be required just to change it from a liquid to a gas. So when we say it has a high heat of vaporization, that's what we're talking about. It takes a lot of energy to change it. And that's, again, why that would suck all the energy out of a fire, right? And this is exactly why. Remember how the other day I was talking about steam is so much more dangerous? Because all of this extra energy is going to be released into your skin, into the environment. If you have steam hit you and it condenses, because it goes back the other way too, right? So you would have, if you're going back in that direction, right, you're going to end up having 2,259 joules of energy going back into your finger, right? So you don't want that steam turning back onto your finger. Now, this made me think of the leaving frost effect, right? Like, isn't it steam that's surrounding your finger? Oh my goodness, questions, questions, questions. Science always brings up more questions than answers sometimes, right? All right, so here I've got a beaker of water, and it's an ice water, and yet the flame underneath it is not making this thing completely, just disappear. In fact, if I would think about this, this, oh, what is it? Silly little spikes. Wow, it's a spiky pen. This water right here is going to be 0 degrees Celsius. If I'm stirring this really, really well, it's going to be 0 degrees Celsius until all that ice melts, because all the energy is going into converting that solid water into liquid water. Okay, so I'm heating this thing up, and yeah, that heat is transferring, but that heat is transferring not to raise the temperature of this water completely. It's got to move that energy into the ice cube, and then that energy is basically going and it's being added to change the ice cube into liquid. Now, again, if I'm stirring this really well, you'll see that true. This thermometer just stays at 0, okay, even though I'm heating this thing up ferociously. But in a situation like this where I'm not stirring, yeah, you're going to see the bottom layer here get warmer, right? And then it's going to have some convection currents. It's going to raise up and heat the ice up, and then it'll cool down again. But isn't that cool? Your thermometer would stay at 0 degrees Celsius even though you're heating this. And the same thing happens with balloons. I always love doing a little experiment with the balloon, and you put the water in the balloon, so it's a little water balloon, and then you put a flame right on it, and the rubber, which would normally like melt under the flame, it's fine. Okay, the balloon doesn't pop at all because all the energy is going from the flame through the balloon into the water, and the water is just absorbing all that energy. It's really cool. Ask me to show a demo sometime if you come back in class. All right, and boom, boom. All right, so we're just kind of showing that same thing. We want to show how the heat from the flame is actually transforming and breaking this bond, okay? So that's kind of what we're showing here. We're showing that as you are heating this stuff up, the hydrogen bonds between the water molecules are breaking. And so sometimes they're escaping and they're leaving, and sometimes they're causing the water to break up, going back and forth until it finally turns into its own 2 separate molecules. Then spaces out, right? Turns into a gas bubble, right? So what is boiling? It's that idea that you're creating bubbles, all right, under the surface of the water due to the gas expanding. And when you finally hit boiling point, you've gotten to a point that is equal to the vapor pressure in the atmosphere. Sorry, the vapor pressure is equal to the atmospheric pressure, and it's escaping. Anyway, lots of cool stuff in this section, and your book is like a paragraph about this. But you just got to talk more about water than just talk about it for the paragraph, because there's so much cool stuff about it. So this is a bonus lecture, better than the textbook, more for you than you would have had if you just read the textbook. So hopefully you enjoyed this lecture. Let's see if we learned what we were set out to learn. Can we explain how certain properties of water are determined by its structure? Absolutely. Like we can talk about, the density, how it changes because it's got to space out because of those hexagons, and how it forms those beautiful ice crystals due to hexagons. We can talk about that insulating property because it's filled with nothing. We're filled with air, and so that is actually why that ice layer is actually pretty insulating in a lake and things like that. So many more things we can talk about there. Let's see if we have criteria for success. Now, given a property of water like the high boiling point, okay, high boiling, 100 degrees Celsius, that's a pretty high boiling point compared to like alcohol or maybe some other things, right? Given a property of water, describe how the structure contributes to determining that property. Why is the boiling point so high? Because those hydrogen bonds, remember, hydrogen bonding is the highest type of intermolecular force that we have, and those hydrogen bonds are holding that water together. So you got to pump up a lot of energy, and you got to get it all the way up to 100 degrees Celsius to get those hydrogen bonds to break, right? Another property, given the property of water, density of the solid form, for instance, describe how that contributes to its property. And again, life on Earth, right? The life on Earth can actually be sustained due to the fact that the water's density as a solid is less than that of a liquid. That's just one example. We've showed you a couple. I hope you had a good time learning today about water. Water is awesome, and you are awesome. And I hope you are having an awesome day today. And I hope that you will be kind to one another. Go make somebody else's day great. Give them a smile, give them a handshake or a fist bump with your mask on in our COVID times. But go make somebody happy today, and share a little light and love with the people around you, and make this world a better place. Okay? All right. God bless you guys. You have a great one.